Today's lecture is our second on imaging science. Let's look at the objectives for today. We can break our objectives into two groups, image processing in one group and image display in another. There is some overlap between the two groups. Our first objective is to learn about medical images and how they are processed. We shall learn about image filtering, reconstruction, and how to display large volumes of images using tile and stack modes. We will also learn about reformatting methods like multiplanar reformatting, 3D display modes using volume rendering, and shaded surface displays, as well as maximum intensity projection. The second group of objectives is to learn about how medical images are displayed. We will look at the technology of cathode ray tubes and liquid crystal displays, and also their viewing conditions. We will also look at performance metrics and enhancements using lookup tables. We will spend some time on display functions and the DICOM GSDF standard. So let's start with image processing. Why do we need image processing? To answer this question, let's consider an image in two dimensions like a chest radiograph. The image is acquired, for example, on a digital detector, and individual pixels are read off and an image displayed on a computer monitor. The left image shows how a chest radiograph would look if we just acquired and displayed it without processing. The right image is what it looks like after processing. The image on the right is clearly more useful. So we can say image processing allows information contained in images to be displayed in more useful forms. However, it is important for us to understand that image processing cannot increase the amount of information available in an input image. So image processing is always limited by the quality of the input data. Image processing involves the use of mathematical operations like convolution. I mentioned convolution in the previous lecture. Applying mathematical operations to images can only remove information present in an image, but that is not necessarily a bad thing. Sometimes removing information that is not relevant can make it easier for humans to understand images. Let's go to the next slide to look at a type of image processing called spatial filtering. Due to the nature of image formation, medical images often have a grainy appearance called quantum mottle. This grainy appearance can be reduced by spatial filtering. Spatial filtering is a smoothing operation that reduces quantum mottle, but it also causes blurring in the image. The figure on this slide shows a chest image with different levels of Gaussian smoothing applied. The highest level of smoothing is shown on the right. The amount of blurring introduced is clear, as you can see. Edge detection and edge enhancement are also applications of interest to us. Let's take a look at edge detection next. Because medical images are complex, they have many discontinuities in the image intensity. Most of these discontinuities are not related to the structure of interest. They may also be discontinuities due to noise, imaging artifacts, or other structures. So one of the main applications of image processing is to detect structures of interest in images. In many situations, the structure of interest and the surrounding structures have different image intensities. By searching for discontinuities in the image intensity function, we can find the boundaries of structures of interest. These discontinuities are called edges. Edge detection algorithms search for edges in images automatically. The figure on this slide shows an MR image of the knee with an edge detected image on the right. This image uses Gaussian derivative filters in X and Y directions. The gradient magnitude image is shown on the far right. The Gaussian plays multiple roles in image processing, as you can see. We can also apply a different spatial filter to enhance the edges of structures in an image by a process called Edge Enhancement. We shall see that next. Here is an application of an Edge Enhancement filter. The first image is the original. The second is a smoothing operation with a Gaussian filter that leads to blurring in the image. The third is an edge enhancement and smoothing operation using a Gaussian Laplacian filter. The Gaussian with the Laplacian function does two things. First, the Gaussian smoothens the image, and second, the Laplacian enhances the edges. Edge enhancement is usually implemented in an algorithm called unsharp masking. We will talk more about unsharp masking in a later lecture. Let's now learn about some image reconstruction methods. Medical images like computer tomography images are commonly reconstructed by filtered back projection methods. Currently, iterative reconstruction methods are also commonly used, and involve a blending of the filtered back projection and iterative reconstruction methods to present a better image quality at the same dose or the same image quality at a reduced dose. Iterative reconstruction methods are either purely statistical or may be model-based. The model-based method is an improvement over purely statistical methods. The top figure shows image B, which is a filtered back projection image, and image A, which is an adaptive statistical iterative reconstructed image. Image C is from a model-based iterative reconstruction algorithm. Note the difference in graininess of the images. An even better method is deep learning. Deep learning involves training algorithms that perform tasks by learning from data-derived patterns and features. Currently, deep learning search methods are becoming more common and overtaking iterative reconstruction methods. Deep learning, like machine learning, is a subset of artificial intelligence systems. Look at the lower figure. The images look almost identical, but if you notice, the left image is actually an iterative reconstructed image at 5 mm slice thickness. The right image is based on a deep learning algorithm of high strength level. This image is reconstructed at 0.625 mm slice thickness. If you were looking at images reconstructed at 5 mm and at 0.625 mm, the noise level will be 2.8 times more in the 0.625 slice thickness, so clearly the image based on deep learning is a better image. Once images are reconstructed, they may be displayed in various formats. There is the tile mode. This is the side-by-side display of large sets of image data. You would need a lot of display monitors side by side to display all the tiles. This became impractical with thin slice image acquisitions and the large number of images that has to be displayed. The tile mode has been largely replaced by stack mode display. In this case, images are stacked on top of each other to allow for scrolling by the push of a keyboard button. This method is useful for following blood vessels and organ boundaries. Besides displaying images, we can also reformat images. Multiplanar reformatting, or MPR, is the reformatting of a volumetric data set into tomographic images. This is done by selecting pixel values from the data set that correspond to the desired tomographic image plane. In general, images are produced parallel to one of the orthogonal planes, axial, coronal, or sagittal planes. In computer tomography, images are acquired in axial planes and reformatted to coronal and sagittal planes. Let's now learn about how coronal and sagittal images are reformatted from axial computed tomography images. Coronal images are formed from axial data sets by selecting a specific row of pixel values from each axial image in the stack of images. Sagittal images are formed from each axial data set by selecting a specific column of pixel values from each axial image in the stack of images. Aside from reformatting to coronal and sagittal planes, computer tomography images can also be reformatted to oblique planes. An oblique image is formed from axial data sets by selecting different rows or columns of pixel values from each axial image in the stack of images. Selection is along a straight line path. The top figure shows an oblique view. The bottom figure shows oblique views obtained from axial images with a thinner slice displayed on the right image. Curved images are formed from axial data sets by selecting different rows or columns of pixel values from each axial image in the stack of images. Selection is along a curved path. Maximum intensity projection is a method of forming projection images by casting rays through a volume data set and selecting the maximal pixel value along each ray. This is illustrated in the top figure. Maximum intensity projection is useful for depicting high signals in a volume, like contrast in CT images or MR studies, or displaying calcified plaque in vessels. 3D viewing is an advantage in imaging modality applications. The two approaches used are shaded surface display and volume rendering. The first step in both approaches is to segment the volume into different structures like soft tissue, bone, calcifications, and so on. Shaded surface display provides a simulated 3D view of the surface of an object in the volume dataset. A major disadvantage of shaded surface display is that only a very small fraction of the information in the original image dataset is displayed. Volume rendering, in contrast to shaded surface display and maximum intensity projection, uses a more complete set of voxels in the stacked axial images. Volume rendering displays more information than shaded surface displays and maximum intensity projection, but may suffer from segmentation errors. Now let's look at how we will display images acquired with two different modalities. Images acquired on two separate modality systems can be co-registered to allow for simultaneous viewing. For example, PET and CT or SPECT and CT images can be co-registered to allow anatomy and function to be assessed. Another aspect of image processing is the use of computer-aided detection. Computer-aided detection uses a computer program to detect features likely to be of clinical significance. It can assist physicians by calling attention to structures that could be overlooked. It is available in mammography to assist in locating structures suggestive of masses and calcifications. It can improve sensitivity, but that leads to reduced specificity. We will talk more about sensitivity and specificity in the next lecture. On the next few slides, we are going to learn about how medical images are displayed. Over the years, we have had two types of displays: hard copy films and soft copy computer displays. Current display systems are often computer monitor displays. Computer displays were traditionally made from cathode ray tubes. These have mostly been replaced by liquid crystal displays. Medical images may be displayed as monochrome or color images. Co-registered dual modality images may be displayed partly or entirely in color. Ultrasound and nuclear medicine workstations usually have color monitors and are able to display cinematic images. A single 1000 by 1000 pixels color monitor is sufficient for ultrasound and nuclear medicine image displays. PET-CT and SPECT-CT images may be displayed on high luminance color monitors. Monitors typically have ambient viewing conditions. For example, areas for viewing clinical images should have a luminance of 20 to 40 lux. A luminance is the rate of light energy impinging on a surface per unit area. It is important for computer monitors to display medical images correctly. Workstation display monitors are evaluated annually to ensure that they all have adequate maximal calibrated luminances and the same display characteristics. Display functions of grayscale monitors and color monitors that display grayscale images are also evaluated to ensure they meet the DICOM GSDF standards, which we shall talk about shortly. One way to evaluate display monitors is to use a test pattern. The SEMTI test pattern is one that is commonly used for monitor QC. SMPTE stands for Society of Motion Picture and Television Engineers. SEMTI test patterns are useful for semi-quantitative assessments of display monitor performance. The American Association of Physicists in Medicine, AAPM, test patterns are also available for monitor assessments. Let's look next at the type of display monitors available. Before current flat panel display monitors became commonplace, most images were displayed on cathode ray tube monitors. You may not see these often now, but for historical context we shall learn about it. If your display monitor is a cathode ray tube, it will consist of a vacuum tube with an anode, a cathode, and a grate between the cathode and anode. A cathode ray tube is like the Crookes tube or X-ray tube we learned about earlier. The cathode is heated to produce electrons that are accelerated to the anode by a 10 to 30 keV potential difference. Flow of electrons from cathode to anode are called cathode rays. The setup is called an electron gun. Electrons are steered electrically or magnetically onto a small area of a phosphor screen. As electrons strike the phosphor screen, light is produced. The intensity of the light on the screen can be changed by varying the voltage signal applied to the grid. A cathode ray tube with a single electron gun displays monochrome images. We will look at the color CRT on the next slide. A color cathode ray tube or CRT has 3 electron guns instead of 1. The screen of a color CRT consists of a triad of tiny dots of phosphors. The phosphors emit red, green, or blue light when struck by electron beams. The phosphor screen has a metal sheet containing holes to allow a single beam to strike a particular phosphor. So one electron beam produces red light, another produces green light, and the third produces blue light. The mixing of red, green, and blue light can create a perception of many different colors for the human visual system. Let's look at how a video signal is formed on the screen. In a cathode ray tube monitor, an image is formed on the screen by quickly steering the electron beam in a raster pattern across the screen. This is the case for both monochrome displays and tricolor displays. If the display is refreshed at between 60 to 80 frames per second, the perception of a fixed image is created. Modern imaging systems now use flat panel liquid crystal displays called LCDs. LCDs are used because of their superior performance and longevity. LCDs have pixels, with each pixel having 3 subpixels whose intensities are independently controlled. So just like a cathode ray tube, different intensities give the perception of color on LCDs. To understand how LCDs work, we need to know that visible light is made of oscillating electric and magnetic fields. These two fields are at right angles to each other, and their intensities can be controlled by two polarizing filters placed at right angles to each other on either side of a liquid crystal layer. LCDs are typically illuminated from behind by visible light. This light falls on one of these two polarizing filters. By controlling the voltage on the liquid crystal's electrodes, different amounts of light are allowed through the polarizing filters to produce different light intensities on the LCD screen. Let's now look at the performance of display monitors. One performance metric of display monitors is specified as luminance. Luminance is the rate of light emitted or reflected from a surface per unit area per unit solid angle. The SI unit is candela per square meter. An older unit called the foot candle is sometimes used. The foot candle is defined as the amount of illumination the inside surface of a 1-foot radius sphere would be receiving if there were a uniform point source of 1 candela in the center of the sphere. The candela itself is an old unit from the time candles were used for illumination. In order to be able to work by candlelight, it was determined that you needed about 70 to 90 foot candles of illumination, which means you need a light from between 70 to 90 candles on the work surface. For grayscale monitors for interpretation workstations, the current ACR technical standard for luminance is 171 candela per square meter for diagnostic radiology monitors and 250 to 450 candela per square meter for monitors used in mammography. There are currently color LCDs providing more than 400 candela per square meters of luminance. An important performance metric is contrast resolution. Contrast resolution is determined by its dynamic range. Dynamic range is the difference between maximal and minimal luminance. Effect of maximal luminance is mixed. Some studies show better accuracy with higher luminance. On the other hand, others have shown that when contrast adjustments like windowing and leveling by an observer is permitted, there is little or no effect of maximal luminance on diagnostic performance. Minimal luminance is also called black level. Black level is the minimal luminance of a monitor measured in total darkness with the entire screen black. LCDs have higher black level than CRTs. Contrast resolution is the ratio of maximal luminance and black level. Another metric for display monitors is veiling glare. Veiling glare is stray light from the face of the monitor that occurs when an image is displayed. This causes a reduction in image contrast. LCD monitors suffer less from veiling glare than CRT monitors. LCD monitors also suffer from lag in displaying dynamic images. This is due to time lag in changing electrical charges stored on capacitors on individual pixels. For LCD monitors displaying dynamic images, a frame rate of greater than 25 frames per second is needed to avoid the perception of flicker. When we spoke about CRT monitors a few slides back, we mentioned that a frame rate of 60 to 80 frames was used to avoid the perception of flicker when displaying stationary images. LCDs, on the other hand, do not suffer from flicker when displaying stationary images. The next performance metric is spatial resolution. Spatial resolution of a display monitor is described by its pixel format with respect to the useful display area. Pixel format is called matrix and useful display area is called field of view. To calculate spatial resolution, you would first calculate pixel size by using the field of view in millimeters divided by matrix. Multiply pixel size by 2 and invert to get spatial resolution in line pairs per millimeter. A worked example is shown. How would the spatial resolution change if you doubled the matrix from a 512 matrix to 1024 matrix for a given field of view? It is desirable for radiologists to view an entire image at or near maximal spatial resolution. To avoid a reduction in spatial resolution when an image is displayed, a monitor should have at least as many pixels in the horizontal and vertical directions as the image. This table shows different pixel formats for different modalities. Digital mammograms and radiographs contain more pixels than other radiological images and are referred to as large matrix size images. Another performance metric is contrast enhancement. Contrast enhancement in medical images is achieved by using lookup tables programmed into medical image processing and display computers. A lookup table is a table containing a value for each possible pixel value in an image. For example, if each pixel could have 1 of 4096 possible values, then the lookup table will have 4096 elements. Here are different lookup tables. The formula used in the lookup table converts the raw digital data into an enhanced analog image at display. The first lookup table in the figure preserves the original image acquisition. The image is low contrast because the useful image information occupies only a small range of grayscale values, but the entire range is being displayed in a linear format. The second shows the modality default lookup table. This is based on optimum grayscale range for a particular modality. Notice that a large portion of the range has been set to 0 or to the maximum and only a narrow range is being displayed. The third shows the display of the entire range of grayscale values from minimum to maximum based on the display system capabilities and is on a sigmoidal curve. The fourth is an inversion achieved by setting the areas that have bright signals to 0 and areas with 0 signal to maximum brightness. The last lookup table is like the default but with the data plotted in a narrower range to enhance contrast. This is for a 14-bit system. A 14-bit system has 16,384 possible grayscale levels. Humans can only perceive up to 30 shades of gray. Let's look at how windowing and leveling ties into the lookup table for contrast enhancement. In this case, the viewer gets to use the entire range of display intensities to display just a portion of the total range of pixel values. This works on either side of the current lookup table. The image here is the high contrast one on the previous slide. It displays a narrow range of intensities. The way this will be displayed is as follows. If, for example, an image has a minimal pixel value of 0 and a maximum of 200, if the user wishes to enhance contrast differences in the brighter portions of the image, they may select a window of say 100 to 200. Intensities from 0 to 100 are displayed as darkest values and 200 and above as brightest values, and values between 100 to 200 will be assigned the intensities determined by the lookup table. On the previous slides, we talked about luminance levels of LCD monitors and also looked at ways to enhance image appearance by using lookup tables and windowing and leveling of lookup table displays. There is a way to tie this all together by using what is called the display function. Suppose you acquire an image and display it on an acquisition workstation that has an inherent display function. This display function describes the luminance produced as a function of the digital or analog signal sent to the monitor. That function is a white curve shown on this figure. Because individual monitors vary in minimal and maximal luminance, this curve will be different on different display monitors. An acquisition system manufacturer may have a model curve built into their system that adjusts the acquired image automatically so that the displayed images have an appearance acceptable to a radiologist when they receive it at the interpretation workstation. But there is a problem. Let's look at the problem and how to resolve it on the next slide. The problem is that a display function on the acquisition monitor varies from monitor to monitor and may also be different from the display function on an interpretation monitor. So images may not be properly displayed when transferred from one monitor to another. To resolve this problem, the DICOM GSDF was created to standardize display of image contrast across different monitors. DICOM stands for Digital Imaging and Communications in Medicine, and GSDF stands for Grayscale Standard Display Function. With this standard, interpretation monitors having identical minimal and maximal luminances will provide almost identical displays of contrast. Note that the DICOM GSDF does not replace user-controlled windowing and leveling. The DICOM GSDF applies only to grayscale images in all formats. It does not apply to color images. Let's look at how we can ensure that all monitors are meeting the DICOM GSDF standard. We can ensure this by calibrating monitors. Display monitor calibration to the DICOM GSDF is usually performed by the monitor itself. Monitor manufacturers provide specialized software and a calibrated photometer that can be used for calibrations. Let's finish up with image display by comparing the diagnostic medical monitor with consumer monitors. Diagnostic monitors have much higher luminance and are more uniform in the display of luminance. They also have smaller pixels, which provides higher spatial resolution. Also, diagnostic monitors have wider viewing angles due to different LCD technology. Let's finish up with a few questions. First question, which of these is a 3D image display method that uses a complete set of voxels in the stacked axial images? Your choices are shaded surface display, sagittal reformatting, volume rendering, filtered back projection. The correct choice is volume rendering. Next question. When displaying CT data, the side-by-side display of large sets of image data is called, and your choices are tile mode, stack mode, volume mode, 2D mode. The correct choice is tile mode. Next question. In multiplanar reconstruction, images are formed by selecting pixel values from one of three orthogonal planes. If the selection is done from a specific row of pixel values, the images produced are, and your choices are sagittal, coronal, axial, oblique. The correct choice is coronal. Next question. Which of these is not an image reconstruction approach? And the choices are filtered back projection, iterative reconstruction, artificial intelligence, AI search methods, maximum intensity projection. The correct choice is maximum intensity projection. This is the last slide. Thank you for watching this presentation.